Lab 3 by Madeline Gaffney. Lab 3 required me to analyze the motion of a star orbiting a black hole and compose a VPython code based on given initial conditions in order to determine the mass of the black hole. The primary concept behind this lab was Newton's second law due to the fact that we use gravitational force and the relationship between the star and the black hole in order to accomplish the objective of the lab. After running the code, which simulated the motion and made calculations based on Newton's second law, I determined that the mass of the black hole was 3.78619 times 10 to the 31 kilograms. In order to initialize the values in the computational model, I used the conditions given to me in WebAssign. The mass of the star which orbits around the black hole is 1.989 times 10 to the 30 kilograms. The start time of observation is 0 seconds, and the time step, or delta t, is 86,400 seconds, or 1 day on Earth. The position of the black hole is 5 times 10 to the 10, 1 times 10 to the 10, 0 meters, and the origin is at 0, 0, 0. The star data file found on WebAssign provided me the star's position time values, which were needed for analysis of its orbit in VPython. Newton's second law is the main physics concept behind this lab. The equation that tells us that force is equal to the gravitational constant times the mass of the star and black hole divided by the distance squared is the most important equation of this lab because it calculates the black hole's mass. In addition to the use of this equation in the code, Newton's second law also contributes the equation that tells us that the net force is equal to the change in momentum divided by the change in time. Since Newton's second law helps us find the net force, it is also essential because it calculates the perpendicular and parallel components of the net force, which contribute to the analysis of the star while in orbit, which we will see later when the computational model is run. Here are the modifications I made to my code. I first updated the initial positions by inserting the star's mass, changing the delta t to 86,400 seconds, and keeping the start time at 0 seconds. I also updated the computation of the y component of the velocity. At the bottom, t equals t plus delta t remains unchanged. This statement causes the code to iterate until the delta t has elapsed completely, which ultimately shows us the star's complete orbit in a day around the black hole. I then updated the equations within the calculation loop. I used the momentum principle where momentum is equal to the mass times the velocity in order to calculate the initial and final momentum of the star during its orbit. I then defined the change in velocity as the final velocity minus the initial, and change in momentum as the final momentum minus the initial. I then defined dp dt as the change in momentum divided by the change in time, which is also equal to f net in the next line. I was able to calculate the dp dt parallel by using the change in momentum calculated earlier as well as its magnitude. I then used the calculation of dp dt parallel subtracted from dp dt to find dp dt perpendicular, or the f net perpendicular, which was then used for the black hole mass calculation. I changed the size of the arrow scale in order to make the results appear well visually. Lastly, I added the calculation of the black hole's mass using the fnet calculated to the print statement so that when the module runs, Python would display the result of the calculations as well. Here's the model that results when I run the code I created. The green curved line represents the star's orbit around the black hole over 1 day. The yellow arrow represents the perpendicular net force of the star, the black represents the parallel net force, and the blue represents the total net force. As the star orbits, these arrows change direction in order to accurately reflect the direction of the net force on the object while it is in motion. I found the mass to be 3.78619 times 10 to the 31 kilograms. If the black hole whose mass I determined through this lab were removed and replaced by another black hole, you would not be able to decipher between the two black holes. This is due to the fact that none of the conditions that factor into the calculation of the mass have changed. The star's mass and motion remain constant, the distance remains constant, and obviously the gravitational constant does not change. As a result, the mass of the black hole would not change either, so you would not be able to tell a difference between the original and new black hole. This question asked me what the difference between the net force and change in momentum over time was. According to Newton's second law, they are equal to each other. The best way to differentiate the two is by looking at them in terms of cause and effect. The net force is the cause of the object's motion since it is the force applied to the object. The change in momentum with respect to the change in time of the object is the result of this force, making it the effect. In conclusion, Newton's second law, as manipulated in VPython, helps create a computational model to find the black hole's mass, which was 3.78619 times 10 to the 31 kilograms.